All right, let's go ahead and see where everybody's at here. All right, we're going to have a theoretical discussion about switching. You two will be a little bit overwhelmed by some of it, so don't just sit back and just listen, because some of it will absorb, it will be good. But don't freak out if you don't know everything, so that's okay. Frank, this is your stuff to dive into. So I'm going to introduce this topic. I'm introducing the concept. There's details that you're just going to have to read about, because I don't have time to dig into all of the details. The details are important. So there are literally, well, and I'll talk about it here in a second. So we're going to talk primarily about a concept called spanning tree. So the spanning tree protocol is pretty much what we're going to be talking about. Spanning tree is really important when it comes to network switching. And we're going to talk about a little bit about that. But just theoretically, I want to talk about something. So in networking, we have these switching devices that we plug our computers into, right? We have so many ports. Like, let's say we have a 24-port switch. And we've got all our computers plugged into them. Well, what happens when we run out of ports and we have to add more machines? The natural inclination would be to add another switch and connect those switches together. Now, as we discussed earlier, we sometimes do that with a crossover cable, but we don't need to do that if the switches are MDIX cables, right? Which is what we just did. So we would cross these over. Now these switches are acting like one fabric. So, or they're basically two switches on the same network, and now I can continue adding PCs. Well, we would add a third, and maybe a fourth, and so on, right? The problem with this is not redundant. This is not a scalable network. If I keep adding switches, right, what happens with one of these cables break? Or what happens when the power goes out on the middle switch? If this cable breaks or this power goes out, then the network up here and the network up here are now segmented. They can no longer talk to each other. So this is not a very good scalable design. Do you know what I mean by the word scalable? Yes. It's not, you can't grow. We can add more machines, but we can't grow the network. Because this is not manageable. I cannot have a device fail and have half the network go down. Right? That's just not feasible. Right? So I had to have a way to have my network scalable and redundant. And so we're going to talk about that. Now there's lots of reasons why networks can have problems. And it's not just failed connections, and it's not just failed switches. There's a lot of things that happen wrong on a network itself. And so we're going to talk about 2 or 3 of those things here as we go. Okay. So the first things that we want to do in a switch network is provide physical redundancy for a physical connection. You see the problem here? One of these drops were a problem. So instead of a configuration like this, the alternative configuration could be something like this. You see that? So in this case, if one switch fails, the only devices that are affected by that switch failure are the ones connected here. These two can still talk. Do you follow me? Or if this cable fails, everybody can still talk because they're still connected. Because I have redundant paths. I can even get more trick by having multiple redundant paths. Do you see that? So I'm creating redundancy in my physical connections. So that's number one very important thing you can do on a physical layer. So on a physical level, and by the way, you should start remembering these terms. Physical is called layer 1. And you'll get that out of your reading here. But physical is layer 1. That's a physical issue. So Switching can be built in a redundant fashion in order to build a redundant switch network that's physically redundant. Okay? The next thing is to build redundancy so that the network cannot be overwhelmed and cause a device to fail because of a layer 2 issue. Layer 2 refers to data link layer. And the data link layer in this case is Ethernet. So Ethernet is a data link layer protocol. The Ethernet protocol can have several things go wrong with it that can cause our switches to go down. There are 3 primary things that can go down with an Ethernet network that we need to be aware of. The first is we can have a MAC database instability. The next one is a broadcast storm. And the third is that multiple frames get transmitted at the same time. Those are the 3 major things that will go wrong on a network. See, little did you know when you were at home connecting to the internet that all these things could be going wrong, right? So these are 3 things that could go wrong on a network. And so we want to be able to overcome the physical, layer 1, and also overcome Ethernet problems, or layer 2. So that's what the goal of redundancy is in networking. And we do that with primarily one protocol, and that's called spanning tree. Okay? So let's talk about MAC database instability and stuff like that. Okay? Maybe you've already figured it out. What is theoretically wrong with this diagram as opposed to this one? This is kind of like a bus, right? It's just like a simple bus topology. It's like a line, right? But what's wrong with this one? What is this? This one, if I were to draw it out, looks just like a line. What would this one look like if I were to draw a simple shape? It looks like a circle, right? So what just fundamentally do you think is wrong with that concept?
You're going to have the same data going around, or one way or the other, because when you're going into the switch, you're calling for a particular switch and it goes there. If that switch if the address goes to 1 and the 2 at the bottom, it has to send it this way or that way.
So
sorry.
This is creating, you said it basically. You're creating a thing called a loop. Loops in networking are bad. The idea is my frame, remember what a frame is? My frame is going to travel around here, and Ethernet frames never die. Meaning they do not have what we call a time to live, or a TTL. Time to live in networking means after so many seconds it'll go away. Ethernet frames don't have a TTL. That means they live forever, right? So if I have a frame that could potentially live forever, what could I potentially have on this network?
A loop.
A loop. And if I keep sending, what's going to eventually happen? Too much, right? Well, that is overcome pretty easily. And I'm not going to talk too much about that because modern switching doesn't allow that to happen. But there's a bigger problem, and I want to talk about the bigger problem. This is called MAC database instability. So that made no sense to most people who hear that concept. But I want to now explain what that means.
What kind of instability?
Well, I'll show you what the instability is. This is an important concept. It's important for anybody in any one of these Cisco classes to understand. So let's talk about it. Every switching device has what is called a bridge table or a MAC address table, right? The MAC address table is a database. And without getting too complex, the database has 2 simple entries, the MAC and the port. A MAC address, MAC, stands for Media Access Control. The MAC address is assigned to every machine. Let me show you how this works. I have a PC here that is connected to a port, right? Another machine is connected to a port. This machine has a MAC address. Let's say it's 1111.1111.1111. You would never have a MAC like that, but let's just say. And this one is 222.2222.2222, right? This guy would like to talk to this guy. He sends a frame, and on the front part of the frame, guess what he's going to put?
The MAC address.
The MAC address of that machine. The address.
The destination MAC address.
So he's going to put all the 2s in there. It's going to go here, and it's going to hit this guy. This guy's going to open it. And how does this guy know that it's destined for him? He's going to read the frame, and he's going to see 2s, and he's going to go, aha, that's my Christmas present. And I'm going to open it up, right? See, networking is much like Christmas presents under a Christmas tree. Could you imagine the chaos? In my family, there's 3 kids. Could you imagine the chaos in my house if on Christmas Day, all the kids went down there and all the packages, the frames, were all wrapped in the same packaging with no name on the front?
No, that's mine.
Right?
That's mine.
What would happen?
I wanted this.
All 3 kids would start unwrapping presents until they started discovering the contents and start to shuffle and transfer ownership, right? That is not a good way to handle networking. It's not a good way to handle your kids, and it's not a good way to handle networking. I don't want my frames to be going out there and having you deal with it and trying to figure out what it is. I want you to know it's for you. That's called efficiency, right? So when I send you a package, I want you to see that it's for you and you to process it. If it's not for you, I want you to discard it, right? So that's what a MAC address is used for, right? I don't want a frame going to a device unnecessarily. So let's say there's a machine over here, and it's 333, right? I don't want a frame destined for 2222222 to go to 333333, right? So if this was a dumb device, did not have a table, then every frame that hit this port would go to every port. It would broadcast every frame to every port, regardless of the MAC. But switches are smart. They're not dumb. What they do is they say, you know what? This is port 1. This is port 2. MAC address 22222 is on port 2. MAC address 111111 whatever is on port 1. MAC address 33333 is on port 3, or whatever. It doesn't always line up that way. You get the idea. So when this frame comes in, the switch looks at its address list and goes, what port does this guy go on? Oh, it goes to port 2. I'm only going to send the frame out port 2. Do you follow me? Got it?
Oh, yes, absolutely.
Now, if I didn't have that entry in there, it had no 22222, then the switch would flood it to every port until it learns where the MAC is, and then it now knows, and then it'll keep it there. That's how a switch works.
I was trying to think of how the layer 3 switch works, but that'll come later.
Ignore that. All right, you got it? Let's talk about MAC address instability. Here is the problem. Let's say I'm connected to another switch over here, and I'm connected to another switch over here. And these guys are connected together. 1111 comes out here. This guy does not know. In fact, there may be a diagram on this. Let's see. No, there's not. So 1111 comes in here initially. He's going to go ahead and record 1111 as being on port 1. We're all good. He's sending to 22222. The first time it hits the switch, he's not going to have the entry in here the first time. So he's going to flood it out all ports. After it's flooded it, and this guy responds back, it'll now know where the 2222 is at, right? However, that flood is also going to go here, and it's also going to go here. Let's say this guy's connected to port 1, and this guy's connected to port like 10, right? This guy's now going to say 22222 is on port 1. This guy's going to say 2222 is on port 10, right? Make sense? You with me so far? So you can have multiple MACs on a port. So I could have 1111 and 333 would also be on port 1 for this guy. So here it comes, and now I know that 2222 is over here somewhere. So I'm going to say, anytime I want to talk to 2222, go over here. This guy's also going to flood out, hey, 2222, and this guy's coming in on port 6. 2222 could be on port 6. You follow me? So what ends up happening in MAC address instability is when these guys flip-flop between ports so fast and so frequently, they forget where the original 222 was at. And let's say a connection drops here or something like that. This guy thinks the 2222 is now on out port 6, and this guy thinks 222 is out port 4. And port 4 and port 6 are connected together between these two switches. What's going to happen? Let's say a frame comes in going for 22222. What's going to happen? Go to here, go back. Go to here, go back. What have we created? A loop. And eventually it's going to take the network down. Does that make sense?
We just got stuck in that.
It's just going to get stuck. And getting stuck is bad. The only way to stop this is to unplug the power on the switches, plug it back in, clear the memory out, solve the problem. So we don't want this kind of instability. Loops in our network cause more than just frames going forever. Loops in our network cause MAC address instability in the switches. This is a bad problem. We don't want this to happen. This will cause these switches to lock up because it'll just be too much, right? So, and we don't have to reboot our switches all the time. So we have to have a way to prevent these guys from looping and corrupting their MAC address tables, which is what just happened in that little demonstration I showed you. Make sense? Pretty clear problem, right? Next is called a broadcast storm. So let's say we do have this loop, right? This loop going on. So we've got the loop. In fact, I'll flip to the diagram. Here we've got this loop. Now, if we've got a loop, and let's say I send a flood out to, let's say this guy's 55555, right? Plugged into some port over here. And this guy sends out a MAC address for 55555. Nobody knows about 555 yet. Out goes the flood. Now, actually, let me do this better, sorry. When somebody sends an address to the MAC address FFFFF, see, MAC addresses are written in hexadecimal. Hex.
Really quick.
Yeah.
Do they automatically assign MAC addresses, or you assign every individual MAC address?
Every network card is born with a MAC.
Okay, so it already has its own 16 digits or whatever.
Yeah. The manufacturer registers with IEEE, and IEEE gives the manufacturer a MAC address.
Okay.
It's a little bit more complicated than that. They give them an OUI, an organizational unique identifier. So let's say you were Intel. You would register with IEEE, and IEEE would give you Intel an OUI number. That's the first half of the MAC address, right? The second half of the MAC address is the actual MAC, and that is what the Intel would stamp onto their network card. They would manually program that into every network card they made.
So then the second half could be the same then on all the Intel.
No, the
cards.
first half is the same on every Intel card.
And
The second half is always unique.
Gotcha. Okay.
That way we can guarantee worldwide that a MAC address is always unique on every NIC, with some limitation. I don't want to get into that, but the idea is that the concept is that MACs are unique. unless I retire a Mac. You can retire a Mac and reuse it. But that's the concept, right? So the idea is, and anyway, if I wanted to send a Mac, and by the way, MAC addresses are hexadecimal. So you know, hex is you go 0 through 9, and then A, B, C, D, E, F. So those are the numbers. So when you have all Fs,
Base 16.
yeah, when you have all Fs, that is called a broadcast. So let's say this machine sends a broadcast out. The switch is going to forward the broadcast out to all ports. Broadcast is going to go here, right? This guy's going to broadcast at all ports. Broadcast is going to go here. This guy's going to what? Broadcast at all ports. It's going to go here. This guy's going to broadcast at all ports. It's going to go here. This guy's going to broadcast at all ports. It's going to go here. You follow me? Rinse and repeat. And pretty soon, guess what we have? We have a loop, but every time it loops, it adds. Every time it loops, we add another packet, another frame. This is called a broadcast storm. And so the more and more broadcast storms, the more and more broadcasts we get, the more the switches have to handle, and eventually we'll overcome the switch's ability to process that many frames, and the network will fail.
The broadcast comes when there's a new MAC address that the table doesn't have. Is that correct?
Yep. So that's one of the other issues. Next issue. It's really a problem in networking if I have a frame going to a source and I end up having two of that frame of the identical same type or the identical same content. So if I have a frame with double the same content going out there in the network, that would wreak all sorts of havoc, right? So if you have a loop, you could potentially have frames coming to a destination machine that have the identical same content, right?
Content.
The identical same stuff inside of them.
Different addresses.
Yeah. Maybe it was instructions to open up a connection. Then it gets it again, open up the connection again. Huh? Right? So it's getting the same thing twice. Now imagine if you have higher level protocols relying on information it's going to get, you're getting confusing stuff. You're getting duplicates in. That would cause a problem. I'm not going to get into too much more about that, but this is going to cause a problem if we have a network loop. So if I convinced you that network loops are bad,
Yes.
all right, that's all I wanted to do. Introduce spanning tree. STP, spanning tree. So let's talk about what that is about. I'll draw it up here real quick. So spanning tree. If I have my triangular network here, my little example redundant switch network, right? All spanning tree does, every one of these switches has spanning tree enabled on them. They send messages back and forth to each other called BPDUs. These are called Bridge Protocol Data Units, BPDUs. These guys send BPDUs back and forth to each other. The only reason they do this is so they can elect which path, which port becomes disabled temporarily. Not disabled, but not sending data. So they're all going to talk to each other, and through an election process, they're going to find out this port right here is going to be in a non-transmitting state. So guess what I've effectively done?
Disturbed the loop.
I've broken the loop. Problem solved. Does this make sense? That's basically spanning tree. That's the basic understanding. I'm going to run out of time to get any more in detail, but that's the basic understanding of spanning tree. However, this port is still able to send BPDUs. Why, Frank? It's not able to send and transmit user data, like frames, but it's able to send BPDUs.
It's a protocol.
Yeah, but why would it be okay to send BPDUs but not any user traffic?
Sending information about the switch.
Yeah, what information might it be sending?
I'm clear, I'm not clear, or okay to send.
It's
or
basically I'm alive,
Oh, okay.
right? Because what happens if this guy stops sending BPDUs?
Something.
I have to open this guy back up. I have to right? I have to have redundancy, right? So if this guy drops and the BPDUs are no longer being sent, this guy's going to say, hey, we need to re-elect, right? And we're going to re-elect, and this guy's going to become open, now sending user data. Now, that doesn't happen just like that. It takes an election process to occur. But after a few seconds, then everybody starts transmitting again, network back up. Make sense? That's spanning tree in a nutshell. And that's all we're going to have time for. But there are multiple versions of spanning tree. And they have enhancements and improvements. And spanning tree doesn't happen on a single flat network. It happens per VLAN. So that's kind of an interesting subject matter.
Is that different from a couple years ago?
No, it's always been the case. So anyway, we're done for tonight. So thank you two for hanging in there,
Yeah,
even though that was a little bit more complex.
Figure it out.
So you know what to do during the week, right?
Good.
Chapter 2.
Yep.
All right, you'll be good. You got it. Did you finish all of Chapter 1 stuff?
Yeah. Did pretty good on my exam. So after the pretest, I felt like crap.
Yeah.
But, this is what it is.
Good. Well, hang in there. You'll do good.
We'll see you next week, man.
All right.